Quadratic sequences. The definition of a quadratic number pattern is a quadratic number pattern has a constant second difference between consecutive terms. The general form of a quadratic sequence is Tn is equal to a n squared plus bn plus c, where n represents the term position. Let's have a look at an example. We ask to write down the general term for the sequence 2, 5, 12, 23. We know that the general form of a quadratic sequence is Tn is equated to a n squared plus bn plus c. If n were equal to 1, we would get the first term, and that will have a value of a plus b plus c. All we've done there is replaced n with the position number, so we get a plus b plus c. In a similar way, when n is 2, your second term has the value 4a plus 2b plus c. And the third term, 9a plus 3b plus c. We can find the first difference between the terms by saying term 2 minus term 1. And we see that when we say term 2 minus term 1, we get a first difference of 3a plus b. And then to get the next consecutive difference, it's term 3 minus term 2. And we get 5a plus b. And similarly, term 4 minus term 3 gives us 7a plus b. We then find the second difference by taking the differences between the first differences. So if we say 5a plus b subtract 3a plus b, we will then get a value of 2a. Similarly, if we say 7a plus b subtract 5a plus b, we once again get a constant second difference of 2a. So what we're seeing is that when we've got a quadratic sequence, the second difference is constant, and it has the value of 2a. And this can then help you to determine the general term if you are given the numerical values for a specific quadratic sequence. So what we've seen is that the first difference in a quadratic sequence forms an arithmetic sequence or a linear sequence with a constant difference of 2a. Let's now use that to help us work out the general term for the sequence 2, 5, 12, and 23. We first need to work out what the constant first difference is before we work out what the constant second difference is. To get from 2 to 5, we have to add 3. To get from 5 to 12, we have to add 7. And to get from 12 to 23, we have to add 11. This is the row of first differences. Now we see if there is a constant second difference. To get from 3 to 7, we add 4. To get from 7 to 11, we add 4. So we can see that our constant second difference has a value of 4. But we know that the constant second difference always has a value of 2a. So therefore, we can work out the value of a by using the equation 2 times a is equal to the constant difference of 4. Therefore, a, divide both sides by 2, will take on a value of 2. So in the general form, Tn is equal to a n squared plus bn plus c. We know that a is equal to 2, so this becomes Tn is equal to 2n squared plus bn plus c. We now need to find the values for b and c. So we're going to go back to our general form and see if we can use simultaneous equations. Our general form being when n took on a value of 1, we saw that the term in position 1 had the values a plus b plus c, and when n had a value of 2, the term in second position had the values 4a plus 2b plus c. We can use that to help us solve simultaneously for b and c. So we're going to have a plus b plus c is equal to term 1, and we saw that term 1 had a value of 2. We also know that a had a value of 2. So therefore, we get 2 plus b plus c is equal to 2. Simplifying further, we get b plus c is equal to, take your 2 over to the right-hand side, 2 minus 2 gives us 0. So we get that b is equal to negative c, and we can call that equation 1. We now move on to term 2, which has the value of 4a plus 2b plus c. And we can see that term 2 also has a value of 5. Therefore, we're going to give it 4 times a, which is 2, plus 2b plus c is equal to 5. Simplifying further, 8 plus 2b plus c is equal to 5. So therefore, 2b plus c is equal to 5 minus 8, which is negative 3. And we call this equation 2. Now that we've got 2 equations, we can solve them simultaneously. We substitute equation 1 into equation 2. So in place of b, we put in negative c. This becomes 2 times negative c plus c is equal to negative 3. Therefore, negative 2c plus c, which just gives us negative c, is equal to negative 3. So c, dividing both sides by negative 1, is equal to 3. We can then substitute that back into equation 1. We know that b is equal to negative c, therefore b is going to take on the value negative 1 times 3, which is just negative 3. So therefore our general form for the specific quadratic equation is a n squared, where a was 2 plus bn, where b was actually negative 3, plus c. And we've seen that c took on the value of 3. This is the general form for this specific quadratic equation.